And lastly, we will be talking about the math in this topic. As I said, you need to really recite most of the highlighted formula in order to quickly deal with the MC. And hopefully, with this practice, you will be more familiar with the derive of some of the important formula at the same time. And let's start. Firstly, this is somehow out of the syllabus, but then this can help us to understand more about this equation. PV equals to 1/3 NMC squared. In the ideal gas equation, derived from the kinetic theory, then we have P, V is here, right? Move to the other side. In this equation, what does the product Nm means? Then you really have to know what is the meaning of N first, and then M. N is the total number of molecules you have, and then small m is mass of one molecule. So that's total number of molecules times the mass of one molecule is in fact equals to big M, which is the total mass of gas. Alright, so that the answer is A. The mass of one mole of the gas is in fact calculated by NAM, because Na is the number of molecules for one mole, and this is also called the molar mass. If you study chem, you have to know this, and even if you're studying physics, somehow you need to know this. And later on, in fact, we will go through it in more detail in radioactivity, book 5. This is wrong. The number of molecules in unit volume, this is all wrong already. Okay, so that the answer is A. Next, which of the following assumption leads to the factor 1/3 in the equation? And the answer is A, because of random motion. So that we have c squared, hopefully you still remember, c squared equals to vx squared plus vy squared plus vz squared of their mean. Okay, so that c squared is equals to vx squared over 3. Okay, this all based on that this is symmetrical because of the fact that this is random. Okay, and then all these are not the same, are not related. The answer is A. And next, this is not a very popular presentation because you can see density here. Which of the following is not an essential assumption of this? In fact, we are just talking about the assumption, not an assumption, right? Then the number of molecules is large. This is an assumption of ideal gas. The volume occupied by molecules is negligible compared to the container. Yes, this is another assumption. No collision between molecules. No, there are collisions between molecules and also between molecule and container. There are no intramolecular attractive force. Yes, so that the answer is C. Next, we will be talking about the shortcut here, so that we will try to look at the whole page. We have trapped some gas inside, which is helium, and then the key is the piston can move smoothly. The meaning of this will be the pressure is in fact kept constant, which is equals to outside pressure, atmospheric pressure. Has a volume of this is V, but then you can see that the unit here is not very good. This is in cm, so that we have to deal with this later. And then pressure is here, and this is a good unit. PA is a good unit because we are using PA, not kPa. Okay? And lastly, we have temperature here, but you can see this is not a good temperature, so that we change it directly. And the height is here, again not a very good unit, we change it. And the mass of 1 mole of helium, this is the molar mass. And this is again in terms of gram. We don't want gram in physics, we do it in chemistry for gram, but in physics we change it to kg, so that should be in kg. Okay, at the end we try to deal with this volume problem. Because we want to change it to meter cube. Then how to change will be 1 meter cube. 1 meter is in fact equals to 100 cm, and we take cube, so that 1 meter cube is equals to 100 cube and cm cube here. So that we have 1 cm cube is in fact 1 over this number meter cube. Okay, therefore how to change will be, this is 300 and then times 1 over 100 cube. Then we will be able to change it to meter cube here from cm cube. Then this is all our preparation. Now we want to find the number of mole. That means we want a small n here. Then the equation that contains small n will be PV equals to nRT. We put in all the number here, see if it is enough. PV equals to nRT. So that we can find out n to be 0.0120 mole. Right, V6. Then next, we further want to find the root mean square, RMS speed. That means we want to find the small c representing root mean square. We have a lot of ways to do it, but then hopefully you still remember all those equations. And one of the way to be PV equals to 1/3 NMC square. You can have c here, right? Then let's see if it is enough. Now we have PV already, so that we copy PV equals to 1/3 n. Do you have n here? The answer is no, you don't have n here because you don't know the total number of molecules. Then how to deal with this problem will be, in fact, you can change it to mc squared, which is the total mass of the gas. Then is it possible? The answer is now yes, because the total mass of the gas can be calculated by the molar mass. 1 mole of helium is having a certain kg. Then we now have 0.0120 mole times, for each mole, the mass is this one. Then we can have enough information to deal with the whole case. And the key for this whole question will be, you are trying to understand why we can do so. And we can press the calculator and get C to be 1370 meter per second here. That means a very, very quick moving air molecules. And then B1, now the temperature changes, and then again we have to change it back to Kelvin temperature. The cylinder is allowed to reach thermal equilibrium while keeping pressure at this one, because we have mentioned already it is smooth for the piston so that the pressure will be constant. Find the equilibrium position of the piston. That is, you want to find the new height of this. That means you want to find the volume of this. Right? Then, in fact, for your math, you can easily find out with the volume 300, with height is 20, you can easily find out the exact area of the base. That is a circle. But then we can skip this process because we are just talking about some ratio problem, because we are using PV over NT is a constant, so that for the first situation, PV over NT for the initial situation will be equals to the PV over NT of the new situation, and the pressure is the same while the number of mole is also the same, so that you can cross it out directly, and we can change the volume into the height times the base area. We say it as A, so that initially the height is this one times the base area A here over the original temperature, which will be equals to the new height times the same area A over the new temperature. And they get the same A here because it is a cylinder. Then you can, by ratio, find out the new H to be 24.2 cm, which is a little bit higher than before because we increase the temperature. Then here the key will be, you try to focus on this situation. Usually we have done that for so many times before. And then you can also skip the process of finding the cross-section area of the cylinder. But if you want to, you can still find it, then you may feel a little bit more comfortable with exact number. And lastly, this is slowly push back original position. What is the new pressure? You want to find the new pressure, P prime. Right? Then in fact, you know everything already because volume, you know it. It is the original volume. And number of mole never change. R is 8.31, and the temperature you know is 90 plus 273. Then you just want to find a new P, and you use the most original calculation here. V equals to N R T. Then you can find out the new P to be a bigger pressure because now it is hotter, so that the molecules will collide with the container wall more frequently and more violently. Okay, and that's it for the demonstration of this question. Next, we will be looking at the average Ke of the molecules at this part. Then hopefully you still remember, or you try to copy, what is the average Ke first. The average Ke you try to copy will be equals to 3RT over 2NA. Okay, and then let's try to look at the example here. Some gas is sealed, that means number of mole is the same, of fixed volume the same. Now it's heated, temperature increases. Which of statements are true? The pressure increases, then again you have two ways to do it. One way is to think of the molecular motion. Temperature increase, they move faster, the average speed faster, frequency of collision increases and more violently, so that the pressure will increase. You can do it, or you can also talk about the macroscopic, that is, this one is a constant, then volume the same, N the same. When temperature increases, then P need to be increases, therefore P increases. Then this is another way to talk about this situation. Next, kinetic energy increases. Then you know the average Ke is equals to 3RT over 2NA. And then you also know that all these are constant except T, so that when T increases, then average Ke increases. So that this is also a correct statement. Lastly, density increases. Density, you just need to talk about volume. Volume unchanged. Therefore, density unchanged. Okay. No change. So that the answer is C. Next, which of the following can increase the average kinetic energy of a fixed mass? And the only thing that can change kinetic energy is that, you know, the average Ke is just directly proportional to T. No more. No more. So that with this in mind, average Ke is this, and also the average Ke is directly proportional to T only. Only T can change the average Ke, no more. With this in mind, then heating the gas at constant volume must be helping, because when T increases, then the average Ke increases. Done. Increasing the volume at constant pressure, then you really have to try to think of when volume increases at constant pressure, what happened to the temperature. Then again, we talk about this relation. It's a constant, and then we have constant pressure, constant N. When volume increases, then T must increase in order to keep this to be constant. Therefore, temperature increases, then average Ke will also increase. So that this is a correct statement. Reducing the volume at constant temperature, you need not to think of it anymore because it is mentioning constant temperature. Then the average Ke must also be constant. Then this is wrong statement. Then the answer must be C. Next, we will be looking at similar things here. Same on the moon and Earth. Then you really have to understand that what is the main difference between the situation on moon and on Earth. Given that if the temperature and the volume of the gas is unchanged, then the only difference between moon and Earth is that the G, the gravity on moon, is about only 1/6 of G Earth. Okay, so that less gravity. And then the average momentum change, is it unchanged? The momentum change is delta m small v. Okay, and then we know that the m is always the same because we are using the same gas, and then v will not be changed because temperature is no change. Therefore, this whole stuff is unchanged. That means the average momentum change is unchanged. Okay, then this is a the average unchanged. Then this is unchanged. Yes, this is unchanged. Then next, the average KE. Now you know that the average KE only related to temperature. So that when temperature is unchanged, then the average KE is also unchanged. So that this is unchanged, yes. Next, the weight of a molecule. Now then the weight of a molecule is mg, right? M is unchanged. M is unchanged. G is decreased because of the moon gravity. Then the weight is decreased for the weight of the molecules. The mass of molecules is unchanged, but the weight decreases. So that this one is changed. That means this is wrong. Then the answer should be boy here. And next, a mixture of two different ideal gas inside two identical vessels. That means we have two identical containers with two identical mixture, okay, in thermal equilibrium to each other, so that they have the same V. They have no, not change. They got the same V and then same T with each other, which offering physical quantity about two gases in their vessel must be the same. That means the comparing two gases in two identical vessel. Then the pressure. Every time when we talk about a specific thing, we really want to know what is depending on this, so that P, we arrange it to be nR over T, nRT over V, and we know that R is a constant, and then T is the same for both, V is the same for both. But then we never mentioned that we put in the same amount of ideal gas inside the vessel. We never mentioned this before, so that because we don't know what is the number of mole, then we are not sure about this, so that it is not a must to be the same. Next, the number of mole per unit volume. That means now if N over V the same, then we want to make N over V the subject, then we have P over RT. On the other side, R and T is the same, but P, we have mentioned it already in statement 1, because P is not sure, then N over T is also not sure. Then this is not a must to be the same. Lastly, average molecular KE, that must be okay, because what we know is the average KE directly proportional to T, and they got the same T, then they must have the same average KE, same and same. So that the answer is B here. Next, a closed vessel. That means the number of molecules is the same of an ideal gas at a certain temperature, and then this is heated, so that temperature increases until the pressure is 1.2 times of the initial, so that P2 is equal to 1.2 P1. calculate the percentage increase in the average KE, then you really have to know average KE is directly proportional to T. Here you may use exact equation, then you may feel a little bit more comfortable. But if you want to be quick, you may use the fact that average KE is directly proportional to T, so that when T increases, average KE also increase. But in order to be a little bit more comfortable, I try to use the equation method to do it for you. So that the exact equation for average KE is this one. This is average KE1, and then the average KE2 is depending on the temperature too. Okay? And the question didn't mention any change about the temperature. It just mentioned the change in pressure only. So that you really have to know the change in temperature first before we talk about anything else. So that we may have to talk about this. PV goes to nRT. We want to know the situation about the temperature, so that we make temperature as the subject. This is T1 corresponding to P1, and all the other things are the same. And T2 will be having P2 here, and all the other things are the same. That is 1.2 P1. So that what we have is, in fact, the temperature is 1.2 times of the initial. This is what we have. So that we try to put in back here for our calculation. That is why the average KE2 will be 3R, and T1 is 1.2, T2 is 1.2 T1. That means we have, this is 1.2 times of the average KE1. Alright, so that by our simple math, the percentage increase is equals to 20%. New minus old over old times 100%, then we got 20% here. And next, here we have two vessels XY which contain equal mass. That means they got the same big M here of an ideal gas. That means we got the same number of molecules, because we are talking about the same types of gas, so that every single molecules are having the same mass. If you have the same total mass, then you must have the same amount of molecules inside. And the temperature of X is higher, Tx is greater than Ty, while the pressure is equal, so that Px is equal to Py. Which of the following statement correct? Average separation of the gas is greater than that in Y. Now when we talk about average separation, we talk about volume. So that we have R equals to PV over NT. We know that P is the same, N is the same. Then you know that X is higher, so that when temperature increases, you will have more volume. That means Vx is in fact greater than Vy. And given that they have the same amount of molecules, then this will be leading to the average separation of X is greater. This is correct. Spacing X is larger. And this is correct. Next, every gas molecules in X is having a greater kinetic energy. That is wrong, because we have mentioned the word every. It is true that the average KE for X is greater than the average KE for Y, because the temperature of X is higher. But this is a distribution, so that the sum is faster. But X also have some very slow molecules inside, so that's not every. Lastly, the collision frequency F on unit area of vessel of X is equal, so that the frequency of X is equal. Then when we talk about frequency, we must talk about the pressure. They got the same pressure here, but then the average speed for X is larger because the temperature of X is larger. That means for X, they are heating more violently for the molecules. But then they got the same pressure. That means for the frequency for X must be lower than the frequency of Y in order to counterbalance that their heating is more violent, so that at the end they can maintain the same pressure. Right? Or you can also say that at the same time the volume is greater, so that the frequency may be less. So that equal is wrong. And then this is also wrong. Then the answer is only A here. Oh, lastly, for this part, for average KE, we have different temperature. T goes to this temperature and then change to a hotter temperature. Then the change in average KE. You know that average KE, having the equation 3RT over 2NA here, then the percentage change is in fact calculated by new minus old over old times 100%, so that the new average KE will be 3R new temperature over 2NA minus the old one, which is a smaller temperature, over the old one times 100%. And you know, we can have a lot of simplification here, and you just got the pure number and you can press the calculator and get directly that change, which is C, 40.